today's topic is about the solution of a differential equations. So how do we know whether a given solution is really a solution of a differential equation? So on this given topic, so we are trying to differentiate what is a general solution from a particular solution. And we want to verify as well if a given general or a particular solution is really a solution of a differential equation. But what is a solution of a differential equation? A solution of a differential equation is an equation which is free from derivatives, and then it satisfies the given differential equation. So once that solution of the differential equation is substituted together with its derivative, so substituted with the given differential equation. So if it satisfies the differential equation, then that is considered as a solution of a differential equation. So a non-derivative relation between the variables which satisfies the given differential equation is a solution of a differential equation. So there are two types of solution, the general solution and the particular solution. So the general solution is typically the solution that we get once we employ any of the methods in finding the solution of a differential equation. So a solution, so which contains arbitrary constants and which are usually represented by letters. So in our case, we are using C as our arbitrary constant for a given differential equation. And then for higher order differential equation, so we are using a subscript, C1 if there is only one solution, then C1 and C2 if there are two solutions. And then it increases as the order of the differential equation increases. So as long as there is an arbitrary constant on the solution of a differential equation, so that is considered as a general solution. So in this case, there is C1 and C2. So those are the two arbitrary constant. Therefore, that is considered as a general solution. And then the second example would have A, B, and C as an arbitrary constant. Therefore, that is considered as a general solution of a given differential equation. So for application, so whenever we were able to represent a certain system into its mathematical equivalent, and then we satisfy that formulated differential equation, so by substituting initial values, and then if there are no longer arbitrary constants that are involved on the given differential equation, then that is what we are referring as the particular solution. So let's say we are given a general solution, so which is y is equals to x plus c. However, there is an initial value that is given that when this one means that whenever x is equals to 0, so y is equals to 3. And substituting those values to our general solution, we'll be able to get the particular solution in exact. In this case, that would be 3. So therefore, once we substitute that one, so giving us y is equals to x plus 3, that is the particular solution. And its general solution is x plus c. Okay, so that is the difference between the general solution and the particular solution. So general solution is more taken. So once we employ the different methods in finding the general solution of a differential equation, and then once we substituted the initial values, we'll be able to determine the value of our arbitrary constant c, and then appending that computed value, so arriving into the particular solution of a differential equation. And in expressing our solution, so aside from the general solution and particular solution, the manner of writing our solution would be either explicit solution or an implicit solution. So if our dependent variable y is expressed in terms of all our independent variable, then that is considered as an explicit solution. So there's only one y, there's only one dependent variable, and then it is expressed in terms of x. So therefore, that is an explicit solution. So typically, that is our requirement, okay, in finding the solution of a differential equation. However, there are cases that it would be difficult to combine our dependent variables. So in such cases, so we are accepting as well the implicit solution. So when we say implicit solution, so that would be a solution involving the relation of the variable and independent variable not explicitly formed. So in this case, the value of y is present. Okay, so in the given solution, so y is not okay, so y is not combined, although we can actually combine this one. So if I am going to factor out y there, so giving me x e raised to x plus 2, then from there plus x equals to c. So if I want to express this one explicitly in terms of y only, so that would give us equal to c minus x all over x e raised to x plus 2. So again, we have the dependent variable 1 expressed to all our independent variables. In this case, it's only x actually. Okay, so it depends. Although the explicit solution would be better, but there are cases that the solution could not be expressed explicitly. So in those cases, implicit solution will be fine. So let's proceed with some of the examples for the solution of the differential equation. So it says here that on the first example, so verify the indicated function, whether that would be a solution of the differential equation or not. So we are given here that dy over dx is equals to xy raised to 1/2. And then y is equals to 1 over 16 as the solution, x raised to the 4th. So let me write it there. So it says that dy dy over dx, so that will be equal to xy raised to 1/2, xy raised to 1/2, and then it says there that our solution is actually equal to 1 over 16 x raised to 4. 1 over 16 and then x raised to 4. Am I correct? X raised to 4. Okay, so let's verify this one, whether that is a solution of the differential equation or not. So in here, so there is y that is involved and we already have y. However, there is a dy over dx there. So we need to derive this one with respect to x. So giving us dy over dx would be equal to. So the rule on how to differentiate, so that would be 4 over 16. That would be 1/4. Alright, so 1/4 and then x raised to cube. So dy and then x raised to cube. And then, so once we already have dy over dx, so we can now substitute that dy over dx is 1/4. Then x cubed is equals to, then x, in this case our y is 1 over 16. Then x raised to 4, right, and then raise it to 1/2. So 1/4 x cubed then is equals to x, and then 1 over 16 raised to 1 half. Okay, so in short, that would be the square root of 1 over 16. Square root of 1 over 16 is 1/4. And x raised to 4 times 1 half, so that is x raised to 2. And thus, so giving us that, that would be 1/4, then x raised to 3. And thus, satisfying our given equation, and therefore, it is a solution. So that's it for our first example. So for our first example, it is a solution of the differential equation. So next is we're going to verify the indicated function is a solution of the differential equation in this given interval. So we have y double prime minus 2y prime plus y. So we have y double prime, let's get minus 2y prime plus y is equals to 0. Y double prime minus 2y prime plus y is equals to 0. Then y is equals to x e raised to x. That would be x e raised to x. So y double prime minus 2y prime plus y is equals to 0. And then our particular solution would be a y is equals to x to e raised to x. So therefore, we are just going to substitute it. But there is a second derivative that is involved. So let's try to derive it first. So y prime will be u dv plus v du. So our u here is x, and then our v is ex. So remember that y prime is u dv plus v du. So our u here would be x, so the y prime then would be u, so which is x, and then derivative of v, it's still e raised to x, and then plus v, so it's e raised to x, and then the derivative of u, so that would be equal to 1. So y prime then is equals to x raised to ex, and then plus e raised to x. And similarly, so we can compute for the second derivative. So the second derivative of x e raised to x is similar as this. That would be x e raised to x plus e raised to x. And then the derivative of e raised to x would still be e raised to x. So therefore, our y double prime then would be x e raised to x plus 2 e raised to x. X e raised to x plus 2 e raised to x. So let us satisfy. So y double prime, so x e raised to x, and then plus 2ex, 2ex. Then minus 2 y prime plus or minus 2, and then our y prime is equivalent to x ex, then plus e raised to x, and then plus our y is equals to x e raised to x, and that should be equal to 0. So giving us x e raised to x plus 2 e raised to x minus 2x e raised to x, and then minus 2 e raised to x plus x e raised to x equals to 0. Then from there, so x e raised to x plus x e raised to x. So this one, so x e raised to x and x e raised to x. So that would be equivalent to 2x e raised to x, and that would cancel out that one. Then 2x minus e2x. So giving us a 0 to be equivalent to 0. And thus, it is a solution of the given differential equation. Let's have example number 3. So it says here that find the value of m so that the function y is equals to e raised to mx is a solution of the given differential equation y prime plus 2y is equal to 0. So we have here that the solution of the differential equation is e raised to mx, and then our differential equation is y prime plus 2y. And then from here, the first derivative of y would be e raised to mx, and then the derivative of mx. Okay, so it's the same as what is the derivative of 2x. Its derivative is 2. So in this case, emx. So for mx, the derivative then would be m. So e raised to mx, derivative of mx is m. So giving us m e raised to mx. And then substituting those values to y prime. So m e raised to mx plus 2y. And then our y is e raised to mx is equals to 0. And then factoring out e raised to mx, so giving us m plus 2 would be equal to 0. And then m plus 2 then would be equal to 0, so therefore m is equals to negative 2. And thus our solution would be y is equals to e raised to negative 2x. Okay, so to further verify so whether really that is a solution or not, so let's try to find what's the first derivative of this. So which is negative 2 e raised to negative 2x. So y prime is negative 2 e raised to negative 2x, and then plus 2. And then y is e raised to negative 2x equals to 0. Therefore, 0 is equals to 0, so which satisfies our given differential equation, and thus our m here is equivalent to 2, and then our solution would be y equals to e raised to negative 2x, which satisfies our given differential equation. So let's proceed with our last example. So we have find the value of m so that the function y is equals to x raised to m is a solution of the given differential equation xy double prime plus 2y prime is equals to 0. So we have x y double prime plus 2y prime equals to 0. And then, so we are to find the value of m. So given that y is equals to x raised to m. So what's the value of m for that? So in this case, we are given the first derivative of y and the second derivative. So it is only proper that we should be able to get the first derivative of x raised to m. So the derivative of this would be using power formula. So that would just be m x raised to m minus 1. Right? And therefore, the second derivative then would be m multiplied with m minus 1, and then x raised to m minus 1, and then minus 1. So that would be m minus 2. So substituting those values, so giving us to have x, and then y double prime is m times m minus 1, then x raised to m minus 2, then plus 2, y prime is mx raised to m minus 1. That would be equal to 0. And then from here, so m minus 1, so combining x, so the base is the same, so it only have 1 there. So m minus 2 plus 1, so giving us x raised to m minus 1. So similarly, I'll have 2m x raised to m minus 1 would be equal to 0. So factoring out x raised to m minus 1, so that will yield to m times m minus 1, then plus 2m. And that is equal to 0. So x raised to m minus 1 then would be m squared minus m, right? Then plus 2m is equals to 0. So x raised to m minus 1 then would be equal to m squared, and then that will be negative m plus 2m, so we'll have plus m is equals to 0. So x raised to m minus 1 then, so we could factor out m, that would be m plus 1 is equals to 0. So therefore m1 is equals to 0, and then m2 would be equal to negative 1. So for our solution then, so we have y is equals to x raised to 0, and then the other solution would be y is equals to x raised to negative 1. So those are the two solutions of our given differential equation. Okay, so 1 over x, or this one is equivalent to just simply 1. Okay, so that's it for our topic on how to verify the solution of a given differential equation.